Hi everyone. We are getting really close to the end of Unit 7, which is going to be the last unit that we're going to cover for AP Chem. So we have sort of two more things to talk about. And one of those is the last thing that we're going to talk about in terms of factors that affect solubility. And in this case, we're going to be talking about pH, so how the pH or the acidity of a solution affects the solubility. So in general, the solubility of a compound containing a basic anion is going to increase as the solution becomes more acidic. All right, so if we take a look at, for example, lead fluoride. So lead-2 fluoride will dissociate into lead-2 ions and 2 fluoride ions. As it turns out, this fluoride ion is slightly basic, and it's going to react with the proton in an acid to form HF. So what that does is it reduces the amount of fluoride ion in solution, and according to Le Chatelier's principle, that's going to shift the equilibrium to the right to form more ions, and more of the lead fluoride will dissolve. Now, the question we have to ask ourselves here is, how do we know if we've got an anion in solution that's going to act as a base? So we need to talk a little bit about acids and bases. So going back to sort of the most basic definition of an acid or base is the Arrhenius definition. So in the Arrhenius definition, an acid is a substance that increases the concentration of protons or hydrogen ions when it's dissolved in water. All right, so this would be, for example, hydrochloric acid in solution will dissociate to form hydrogen ions and chloride ions. So this would be an Arrhenius acid. By this definition, a base is a substance that is going to increase the concentration of hydroxide ions in solution. So for example, sodium hydroxide. So sodium hydroxide in water will dissociate into sodium ions plus hydroxide ions. For what we want to talk about, we need to have a little bit more sophisticated definition of an acid and base. And so we're going to use the Bronsted-Lowry definition of an acid and a base. So in this definition, an acid is a substance that donates a proton to another substance. So again, we can think of hydrochloric acid also would be included in that definition of a Bronsted-Lowry acid. So what happens is that this proton doesn't actually just get donated to nothing. It gets donated to a water molecule in solution with the acid. So we can see here we've got HCl and a water molecule, and the HCl is going to give up its hydrogen, and it's going to actually give it to a water molecule to form this H3O plus ion. So that H3O plus ion is what we call a hydronium ion. This is going to be interchangeable with an H plus ion. So when we say H plus in solution, like we've written here H plus, what we really mean is a hydronium ion, which is a water molecule with an extra proton on it. By this definition, a base is going to be a substance that accepts a proton. So in this case, the water molecule is accepting the proton from the HCl. So water is the base in this reaction. Bronsted-Lowry acid-base proton transfers don't have to occur in aqueous solution, so you don't have to have water there to accept or donate a proton. For example, we could take hydrochloric acid and put it in a different liquid, in this case ammonia, NH3, and we can see that the HCl will still donate its proton, acting as the acid, and the NH3 will accept the proton, acting as the base and becoming NH4+, an ammonium ion. All right, so here HCl is the acid, NH3 is the base. When we think about an acid-base equilibrium, we have to remember that both the forward and reverse reactions are happening, and both of them are going to involve a proton transfer. And so what happens is that your acid in the forward reaction is going to become a base in the reverse reaction. So let's take a look at an example of this. So let's say we have just some acid here, HX, and we add it to water. HX, our acid, will donate a proton to the water. HX will become X minus, and the water will become a hydronium ion, H3O+. In the forward reaction, HX donates a proton to act as an acid, and H2O acts as a base in accepting the proton. However, if we look at our reverse reaction, we can see that the opposite's going to happen. Now this X minus is going to accept a proton from H3O+. All right, and so we have to introduce a new vocabulary term here, which is a conjugate acid-base pair. When you have an acid and a base, like HX and X minus, that only differ in the presence or absence of a proton, we call that a conjugate acid-base pair. All right, so HX is the same thing as X, except that it doesn't have a proton anymore. All right, so this X minus has lost a proton, but other than that, they're the same. And in the reverse reaction, this X minus is acting as a base by accepting a proton from hydronium to turn back into HX. So that X minus we would call a conjugate base. On the other hand, water acts as a base on the forward reaction, accepting a proton, but in the reverse reaction, this hydronium ion is going to act as an acid in donating the proton. And so because it's the same as water, but with one extra hydrogen, we would call that the conjugate acid of water. All right, so HX and X minus create what we call a conjugate acid-base pair, and water and the hydronium ion also create a conjugate acid-base pair. This information is really important in figuring out whether or not our compound is going to be more soluble in an acid, because those conjugate acid-base pairs are going to tell us whether or not our anion is basic. All right, so basically the way that this works is that the conjugate base of a strong acid has negligible basicity, so it is not a base. So if you've got a strong acid, its conjugate base is not a base. Okay, it's not going to react with hydronium and increase the solubility of your compound. On the other hand, if you've got the conjugate base of a weak acid, that's going to be a weak base. All right, so if you have a weak acid, its conjugate base will act as a weak base. It'll react with acid in solution and increase the solubility of the compound. All right, and then our final situation, the conjugate base of something that is not acidic will be a strong base. So if you take the conjugate base of something that is a really, really, really weak or negligible acid, then the conjugate base will be a strong base. So it's opposite, basically. The stronger the acid, the weaker the conjugate base. And you can kind of see that here. So if we've got a really strong acid over here, then the conjugate base will be really, really weak. If we've got something like water that's really not an acid, then its conjugate base, OH, is going to be a really strong base. And if we look at something in the middle, so for example, hydrofluoric acid is a weak acid, then its conjugate base will be a weak base, but it will act as a base. In order for this information to be helpful to you, you have to remember the strong acids. So we talked about this earlier in the year, but the 7 strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, chloric acid, perchloric acid, and sulfuric acid. Okay, so back to thinking about what this has to do with solubility and our solubility equilibria. All right, so in general, anytime you've got an anion, X minus, that can be considered to be the conjugate base of an acid. So add a hydrogen back onto that and consider that acid conjugate base pair. And so whether or not that anion is going to react with water to form OH depends on the strength of the conjugate acid. So if you add an H back to your anion and it becomes a strong acid, then that anion will not act as a base. It'll be a negligible conjugate base. All right, so let's take a look at some ionic compounds and decide whether they're going to be more soluble in acidic solution than basic solution. So we're going to consider nickel hydroxide, calcium carbonate, barium fluoride, and silver chloride. All right, so taking a look at nickel hydroxide, our first example here. The first thing that we want to do is consider our equilibrium here. So what is this going to dissociate into when it dissolves in water? So that's going to be nickel 2 plus 2 hydroxide ions. All right, so we're looking only at the anion here. So this hydroxide ion, you should already know, if you see hydroxide ion, you should know that this is going to act as a base, but we can still consider its conjugate acid. So the conjugate acid of OH is going to be H2O. It's the conjugate base, but with another hydrogen, right? So if I've got 2 hydrogens and an oxygen, that's water, okay? Water is a negligible acid. right? So you know water, you drink it, it's not acidic, right? So if this is a negligible acid, that means that the conjugate base is going to be a strong base, okay? And if we have an anion that's acting as a base, it can react with acid and get removed from solution. So if we put this in an acidic solution, we're going to remove hydroxide from the solution. Our equilibrium will shift towards products, and it will become more soluble. So more of the nickel hydroxide will dissolve in acidic solution. So this is going to be more soluble in acid. All right, because the anion that it forms is a strong base. So let's look at the next one here. So calcium carbonate, we want to do exactly the same thing. It's going to dissociate into calcium ions plus carbonate ions. So the question here is this carbonate ion going to act as a base? All right, so we want to look at the conjugate acid. So what is this anion if we add a hydrogen to it? So the conjugate acid here is going to be HCO3 minus. So we've added one hydrogen. That's going to take the charge from -2 to -1. This is our conjugate acid. And if we think about our list of strong acids, this is definitely not one of them. All right, so this is going to be a weak acid, which means that our carbonate ion is going to be a weak base. So remember, it's not an opposite situation. It's not like weak acid means strong base. If it's weak, they're both weak. If one of them is strong, like we had up here, the other one is, like if this is a strong base, this is not an acid at all, right? So it's negligible acid. So weak acid means it's also a weak base, okay? And if this is a weak base, that means that it can react with acid, push that equilibrium towards products, and dissolve more of the calcium carbonate. So this one is also going to be more soluble in acid. Okay, so following the same set of rules, I want you to pause the video and see if you can figure out if barium fluoride and silver chloride are going to be more soluble in acid. And once you think you've got answers, go ahead and continue the video. All right, so taking a look at barium fluoride, we're going to dissociate into barium ions and 2 fluoride ions. Let's check out the conjugate base of fluoride. That's going to be HF, hydrofluoric acid. We want to remember that that's a weak acid, which means our conjugate base is going to be a weak base. All right, if we've got a weak base in our solution, then barium fluoride will be more soluble in acid. So adding acid, again, we're going to shift our equilibrium. We're going to remove fluoride, which is going to shift our equilibrium and cause more of the barium fluoride to dissolve. Now, for silver chloride, we're dissociating into silver ions and chloride ions. Taking a look at the conjugate acid of chloride ions, that's going to be HCl, hydrochloric acid. That is a strong acid, right? So this is on our list of strong acids, which means that its conjugate base is not going to be a base. So Cl minus will not act as a base. If we add acid to the solution, it will not react with the chloride ion. So it will not affect the equilibrium, and silver chloride will not become more soluble in acid.